Hi, everybody. Welcome back. I noticed that we weren't quite finished our 4.3 notes that we started before spring break. So we went through all of this, and we got all the way down to page 12. Oh, that looks like this. It talks about points of inflection. Okay, so here's the definition. A point of inflection is a point where the graph has a tangent line line and the concavity changes. And concavity usually comes down to the second derivative and what's happening with that. And so if f double prime of x is equal to 0 at a certain point, then you get what is called a possible horizontal inflection point. And the second bullet point is this: if f double prime of x does not exist, then we get a possible vertical inflection point. And we must check these situations. Okay, so basically a point of inflection is where concavity changes. Remember we talked about parts of the graph that were concave up like this, and we think of it as holding water. And then there's a certain point where concavity will switch to where the graph is then dumping water, right? And so this point here where concavity switches, that is the inflection point. Okay, so that's all we're talking about. Okay, so this little section is what we call concave up. Happy holds water, and this section is concave down, dumps water. All right, so let's do an example. Example 3, finding the points of inflection. Determine the points of inflection for the curve y equals 3 plus sine x on 0 to 2 pi. If we do a quick graph, sometimes with these it's pretty nice to see on the graph. Here's my y-axis, there's the x. Y equals 3 plus sine x is just a sine x graph that has been moved 3 up. Normally the sine x graph starts at 0, 0, so it's going to go 1, 2, 3. I'm just going to fix this a little bit so that it's not too high up there. Okay, So this 3 plus sine x is going to start there. And we're going from 0 to 2 pi. Cut the interval in half, and then cut the interval in half again. So 1 pi over 2, 2 pi over 2. This is 3 pi over 2. And of course, 2 pi is 4 pi over 2. And the sine graph starts in the middle, then it goes up to the high point, goes back to the middle, down to the low point, and back to the middle. Okay, so determine the points of inflection for the curve y equals 3 plus sine x on 0 to 2 pi. It looks to me, just from looking at the graph, that it's going to be this point right here, right? That's where concavity switches from concave down to concave up. Okay, so graphically, that looks like the spot. Here's how we do it analytically. We have to find the second derivative of the function and then find where that equals 0. So the first derivative, first of all, is the derivative of 3 plus sine x. The derivative of 3 is 0. The derivative of sine x is cos x. And then the second derivative of that, the derivative of cos x, is negative sine x. And we want to know, where does negative sine x equal 0? Negative sine x starts at 0, 0 and it goes down like this, right? So this is 0. That would be pi over 2. This is pi. There's 3 pi over 2 and 2 pi. Okay, so where does negative sine x equal 0? This implies that x equals 0, pi, or 2 pi. Okay, and if we look at the interval of our original graph, it's from 0 to 2 pi. We're certainly not going to have, there's not an inflection point at 0 or 2 pi because the graph stops at those endpoints. So we can knock off this. X equals pi. Is our inflection point. And I guess since that's where the second derivative equals 0 and it's not undefined there, then we would technically call this a horizontal inflection point. Vertical inflection point is when the second derivative does not exist, right? If we look up at our definition up above. Okay, so that's our analytic proof, and we can see right here, horizontal inflection point at pi, comma, 3. All right, let's try letter B. Determine the points of inflection for the curve shown there. Okay, so we need to get the second derivative. So the first derivative is negative 6x squared plus 12x. The second derivative is negative 12x plus 12. And we need to know where y double prime equals 0. So I'm going to go set y double prime equal to 0. This means negative 12x plus 12 equals 0, which means that negative 12x would equal negative 12 if I subtracted the 12 over, and then divide both sides by negative 12, and we get an inflection point at x equals 1. And this is a horizontal inflection point because that's the point where y double prime is equal to 0. And if we do a quick graph, negative 2x to the power of 3 plus 6x squared minus 3. Standardize that. And you see it's a negative cubic. And so if I do a quick sketch, looks like it's doing something like this. So at x equals 1, if I were to plug 1 into the original function, it looks like I would get negative 2 plus 6, which is 4, and then 4 minus 3 is 1. It looks like the y value that's associated with this horizontal inflection point is y equals 1 as well. And so right there, there's our point of inflection. And this point here, of course, is the constant of the polynomial, so that's negative 3. Great, so that's a good visual of an inflection point, and you can see that the graph goes from holding water on this side, and then that point right there is where it then switches to dumping water. And we call this concave up, happy, and concave down, sad. Okay, so then we can get on to the second derivative test for local extrema. And this is if f is continuous at C, and so it says this. There's sort of three cases. A, if f prime of C equals 0. That's a special way of saying that C is a critical point. C is a critical point. If f prime of C equals 0, and f double prime of C is less than 0, negative, the second derivative is negative at that point, that would mean concave down. And if something is concave down, then f of C is a relative max. Okay, so C is a critical point, which means it's at the top of a hill or the bottom of a valley. And if the second derivative is negative, then the graph would be concave down at that point. And so that would force f of C to be a relative max, like the little picture I've shown there. Part B, if f prime of C equals 0, so C is a critical point, and the second derivative is greater than 0, then f of C is a relative min. Okay, so you've got a second derivative that's positive, which means the graph is concave up. And so then C is going to be at the bottom of that valley, a relative min. And part C, if f prime of C is equal to 0, and f double prime of C is equal to 0, then we use the first derivative test, which we learned earlier in the notes. Have to just stick with the first derivative test. All right, so let's try an example using the second derivative test. Find the extreme values of f of x. Equals x cubed minus 12x minus 5. So we first need to figure out the critical points of this function. So we have to find the first derivative and find where that equals 0. So the first derivative is 3x squared minus 12. Set this equal to 0 to find the critical points. So 3x squared minus 12 equals 0. Let's divide out the 3. And we have a difference of squares. And so we get critical points, x equals negative 2 and 2. So these are the critical points. These would be the c values, I guess, up above in the second derivative test definition. And then to use the second derivative test, we need to find the second derivative. F double prime of x, it's the derivative of the first derivative, so we end up getting 6x. And then what you're supposed to do is plug your critical points into the second derivative and see whether you get a positive result or a negative result. So our critical points were negative 2 and 2. F double prime of negative 2 gives us 6 times negative 2. Which is equal to negative 12. So we get that the second derivative is negative 12 less than 0 at the critical point, negative 2. So we can say second derivative is negative. So we would have concave down. Concave down, and so C is a relative max. So we can say therefore relative max at the x value is negative 2. If you want to get the y value that goes with that, plug the negative 2 into the original f of x. Looks like we would get negative 8 plus 24, which is 16 minus 5, so 11. So relative max at negative 2 comma 11, or you can call it a local max. F prime of 2, 2 is the other critical point, is 6 times 2, which is 12. That's positive, so the graph is concave up. Happy. And so then we have, therefore, a relative min at 2 is the x value. The y you have to get by plugging into the original function. 2 cubed is 8, minus 24 is negative 16, minus 5 is negative 21. And so that's an example of using the second derivative test. Okay, and we'll finally finish off with example 5. This is using f prime and f double prime to graph the original function f. Okay, and so we're going to let f of x equal 4x cubed minus 12x squared. And part A, identify where the extrema of f occur. Remember, the extrema of f occur either at the endpoints or the critical points. Now, there are no endpoints to this graph. It goes from negative infinity to infinity. It's a John Travolta graph, right? It looks like this. It's a cubic. So it's not going to have an absolute max or an absolute min. So the extrema are just going to be local ones, which will occur at the critical points. So critical points are where the first derivative equals 0. So f prime of x is 12x squared minus 24x. Set this equal to 0. We can divide out a 12 and an x and have x minus 2 left over. So we get a critical point at x equals 0 and a critical point at x equals 2. These are the CPs. That's where the extrema occur. Part B says find the intervals on which f is increasing and the intervals on which f is decreasing. Okay. I'm going to fix this assignment as soon as we're done this example, so let's not circle that. Part B. Intervals of increase and decrease, that comes from the first derivative test. All right, and so that's where you do the little number line. And you plot the critical points at 0 and 2. And we are going to look at f prime and see what that means for f. And so what you do is you plot, or you do like a sketch of f prime. And if I look at f prime, it is 12x squared minus 24x. So that is a positive quadratic. And a positive quadratic is a parabola facing up. Remember, the negative ones are like this, facing down, right? I do it dotted for some reason sometimes, so we would have very roughly positive quadratic like this. And so you can see that the values of f prime are above the axis in this interval, so they are all positive heights, which correspond to positive slopes on the original function. The values of f prime, those are all negative heights here, and in the last interval, they are above the x-axis, so positive heights. And at the critical points, f prime is 0 at both of those points. Okay, which means for the original function, we've got positive slopes for the whole interval, and if something is sloped positively the whole time, then it increases. Negative slope values in the second interval, so the original graph decreases, and then positive slopes in the last interval, so the original graph increases. So we've got increasing on the interval negative infinity to 0, or on the interval 2 to infinity. So that's where f is increasing and the function is decreasing on 0 to 2. Part C, find where the graph is concave up and where it is concave down. That comes from the second derivative. So let's figure out the second derivative. F double prime of x is going to be, I do the derivative of the first derivative, so I'm going to get 24x minus 24. Set that equal to 0 to find the inflection points. Okay, so that is a horizontal inflection point. And then we can do a number line thing as well, and you plot the inflection point. We do a comparison of f double prime and what that means for the original function. So I'm going to graph f double prime, which is 24x minus 24. That's y equals mx plus b, so that's a straight line with a positive slope of 24 with a 0 for x-intercept at x equals 1. So that's what the second derivative graph looks like, and you can see the heights are negative here and positive here, and f double prime hits 0 at x equals 1. Okay, and if the second derivative is negative, then the original function is concave down, sad. And if the second derivative is positive, then we would get concave up, happy. So find where the graph of f is concave up and where it is concave down. So we just found concave down in the first interval. That is from negative infinity to 1. And for some reason with concavity, they just use open brackets, whereas with increasing, decreasing, the endpoints, we have square brackets. Okay, and our original graph is concave up on the interval 1 to infinity. Okay. All right, and so now based on all of that, we should be able to sketch a possible graph for f. Just show shape, not location of points. I like to show some location of points though, guys. So here's what you can do. I would encourage you to start by plotting the critical points and the inflection point. Okay, and so our first critical point was at x equals 0. And if you put 0 into the original function, 4x cubed minus 12x squared, if you put 0 into that, you will get 0 for y. So our first critical point is actually at 0, 0. The second critical point is at x equals 2. And if I put 2 into the original function, you end up getting negative 16. So I'm going to kind of butcher the grid a little bit here. 2 and negative 16. So I'm going to plot that point. And the inflection point is at x equals 1, and if I put 1 into the original f of x, you end up getting 4 minus 12, which is negative 8. So the inflection point is right here. Okay, and so then you'll notice that the original function has to be increasing from negative infinity to 0, and that 0 is a relative max. And then the graph is decreasing from 0 to 2, and we have an inflection point at x equals 1. So decreasing, and then you can see right at that inflection point, it switches concavity. The graph is still going down, and then from 2 to infinity, we have increasing like that. So increasing, decreasing, increasing, and concavity goes from concave down from negative infinity to 1 to concave up from 1 to infinity. Okay, so hopefully you guys can see the concave down nature of this, and then once we hit here, oh, it switches to concave up within this idea of increase, decrease, increase. Okay, so that is the end of our 4.3 notes. I changed the assignment a little bit. Let's get rid of these numbers. Changed it to 1 to 6, 7 to 11 odd, 13, 19, 21, 25, 29. And I have my own handwritten answer key at yolasite.com. Just go into our regular Calc 12 folder. Okay, I have a folder on there that's called Online Learning as well, and I'm going to post these videos and other things, but the answer key is in the regular Calc 12 folder. That's not in the Online Learning one. And the other thing is, if you don't have your textbook, if you left it at the school or something like that, maybe try Open Library. I just Googled Open Library. You have to make an account, but it's not a huge deal. Try Open Library and then search for our book. Like this. Calculus. Graphical. Graphical, numerical, algebraic. And I'm pretty sure we want the 1999 one. Yes. 1991 one. So give that a try. If you have any problems, let me know and I'll try to help you out with that. Okay, everybody, I will send you another video hopefully next week.